AI is often described as a race for chips, but behind every accelerator is a more fundamental requirement: electricity, delivered reliably and at extraordinary density. This briefing follows that hidden infrastructure, from the grid to the chip. We will look at why power has become the next bottleneck, how the architecture is changing, and which suppliers are positioned across the value chain. The central idea is simple. The AI build-out is no longer only a compute story. It is now a power and energy supply chain story. This series is designed to connect company stories with the infrastructure underneath them. In this episode, we are following the flow of power itself, because that is where many of the most important constraints and competitive opportunities are emerging. GPU wattage has risen, rack density has multiplied, and grid capacity has become harder to secure on the timelines AI developers want. Together, those forces have moved electricity from a supporting input to a first-order constraint. To understand the scale of that shift, the next slide reduces the problem to 4 numbers that define the new operating reality. These 4 figures show why legacy assumptions no longer hold. A single NVL72 rack can draw more than 120 kilowatts, over 6 times a typical 2020 rack. At cluster scale, demand approaches 1 megawatt, forcing changes to busway and switchgear. At the same time, the briefing tracks more than $500 billion of data center capital commitments and over 40 gigawatts of planned capacity. Every rack, cluster, and announced gigawatt depends on physical power infrastructure. That is where deployment schedules can accelerate or stall. The response is not simply to install more of the old equipment. The architecture itself is changing. Traditional server rooms were designed around roughly 10 to 20 kilowatts per rack, a C-heavy distribution, and separate power and cooling systems. The AI era baseline moves toward 48-volt KC rack power, high-voltage DC busway, and integrated thermal design. These changes reduce conversion losses and support much denser clusters. In other words, AI is forcing power and cooling to become one coordinated system rather than 2 independent facility functions. That architectural reset is creating a large and sustained market cycle. The figures used in this briefing show the data center power management market growing from $28.7 billion in 2025 to $87.4 billion by 2033. That implies a 15.7% compound annual growth rate, roughly a tripling over the period. The important point is not only the headline growth. High-density power is becoming standard infrastructure, which means demand reaches beyond a single product cycle and into transformers, switchgear, UPS systems, distribution, and rack-level power electronics. Power reaches the chip through 5 distinct links. It begins with the utility, moves through transformers and switchgear, passes into uninterruptible power systems, travels across busway and PDUs, and finally reaches server power supplies and voltage regulation. Each step has its own engineering requirements and supplier landscape. The briefing highlights UPS systems and server PSUs as especially attractive volume and margin pools. This is also where global facility incumbents meet Taiwan's rack power specialists, creating a competitive overlap that becomes clearer when we follow who actually buys the equipment. We have followed the physical path from the grid to the chip. Now the story shifts from components to customers. Power hardware moves through 4 buyer tiers. Chip platforms define the specifications. Server manufacturers integrate the systems. Hyperscalers deploy them at enormous scale. And facility operators keep them running. The same suppliers can appear at several points in that chain. Understanding these relationships matters because volume, qualification requirements, and negotiating power change as we move from the platform level toward the operators managing entire campuses. This map shows why power suppliers cannot be understood through a single customer relationship. Chip platforms such as NVIDIA, AMD, and Intel set the electrical requirements. Server ODMs and OEMs translate those specifications into rack designs. Hyperscalers then deploy those racks at scale, while colocation and neocloud operators provide the facilities. Rack power specialists, facility power companies, and grid interface vendors sell into different combinations of these tiers. As order sizes grow, co-design becomes deeper. The result is a network in which qualification and trusted integration can matter as much as the component itself. The platform companies shape demand even when they do not manufacture the power equipment. NVIDIA Blackwell, AMD Instinct, and Intel Xeon and Gaudi products each impose electrical and thermal requirements that suppliers must meet. Those specifications determine rack voltage, PSU capacity, distribution design, cooling integration, and facility upgrades. This makes the chip roadmap an upstream signal for the entire power supply chain. The next two slides focus on AMD and Intel to show that challenger platforms do not create separate infrastructure. They amplify demand across much of the same supplier ecosystem. AMD and Intel broaden the market without creating entirely new power chains. AMD's high wattage Instinct accelerators require the same kind of dense 48-volt rack architecture used across leading AI deployments. Intel contributes through both Gaudi accelerators and the widespread use of Xeon host CPUs. That means power demand extends through accelerator racks and the supporting compute around them. The key signal is shared qualification. Suppliers such as Delta, Acbel, and Chicony can serve multiple platforms through common ODM channels, concentrating value in vendors that repeatedly meet demanding power and thermal specifications. This diagram makes the convergence explicit. NVIDIA, AMD, and Intel compete at the silicon layer, but their systems draw on a shared rack power base that includes Delta, Acbel, Chicony, and Lite-On. Above that sits a common facility layer led by companies such as Vertiv, Eaton, and Schneider Electric. Shared qualification helps suppliers spread platform risk, while customers gain from proven designs and scalable manufacturing. The strategic implication is that growth across several chip platforms can compound demand for the same power vendors, rather than fragmenting it into isolated supply chains. With the demand structure established, we can now focus on the companies building the hardware. These specialists span server power supplies, UPS systems, busway and PDUs, and grid-level switchgear. Their competitive advantage comes from more than manufacturing capacity. They must deliver efficiency, reliability, platform qualification, and increasingly, integration with thermal systems. The supplier landscape divides broadly into Taiwan's high-volume rack power champions and global incumbents that dominate facility and grid infrastructure. We will start at the rack, where Taiwan has built a particularly strong position. Taiwan's power electronics ecosystem sits at the high-volume edge of the AI rack. Delta has the broadest position, combining power and cooling across much of the stack. Acbel and Chicony bring deep server PSU expertise and shared platform qualifications. Lite-On is expanding into integrated power and thermal systems, while Zippy remains a specialist in rack mount and redundant supplies. Their advantage comes from qualification depth, manufacturing economics, and proximity to the server ODM ecosystem. As rack density rises, that combination turns long-standing electronics expertise expertise into strategic AI infrastructure capability. At the facility and grid layers, the competitive set shifts toward global incumbents. Eaton combines rack distribution, UPS, and broader grid-to-chip ambitions. Vertiv and Schneider Electric are central to high-density facility power, distribution, management, and thermal infrastructure. ABB and Siemens Energy anchor transformer and switchgear capabilities, while Flex provides high-volume contract manufacturing for server power. The critical point is timing. A data center cannot come online before its physical electrical infrastructure. Transformer and switchgear availability can therefore set the deployment calendar, regardless of how quickly chips or servers are ready. The market rewards two different forms of strength. Full-stack companies can capture more value across each rack and facility because they participate in several layers. Specialists can still win by being exceptionally efficient, deeply qualified, and able to manufacture at scale. That creates a tension between breadth and depth. The final comparison brings those positions together across server PSUs, distribution UPS, grid interface, and facility management. It shows who can offer an integrated architecture and where focused suppliers remain essential despite operating in fewer layers. The coverage matrix makes the strategic split visible. Delta Electronics and Eaton are the only companies in this briefing shown across all 5 layers. Vertiv and Schneider Electric have strong positions in distribution, UPS, and facility management, while ABB and Siemens concentrate closer to the grid. Taiwan's Acbel, Chicony, Lite-On, and Flex remain more focused on rack-level power and manufacturing. Breadth offers more value capture and system influence, but specialization still matters where qualification, efficiency, and volume are decisive. The winners will combine the right footprint with execution in the layers that constrain deployment. The larger story is that power delivery has moved from the background to the center of the AI build-out. The industry needs more than faster chips. It needs utilities, transformers, switchgear, UPS systems, distribution, rack power, and cooling to advance together. That shift creates bottlenecks, but it also creates a broad new field of opportunity for the companies that can deliver reliable infrastructure at scale. Thank you for watching. See you in the next.